wing, right? And so these engines provide you with thrust. So for any of you who've been on a plane before, you probably remember during takeoff, you're just sitting there and then all of a sudden you push back into your seat, right? You start accelerating down the runway and eventually you take off. So the thing about a plane is it has propulsion. So this has its own propulsion system. And with a glider, it does not. So we do not have propulsion. So I'm sure many of you have made paper airplanes before. Paper airplanes do not have propulsion. Your hand, when you throw it, is the only propulsion you're going to get. When you let go of that, it's on your own. So that's where we get the term glide, because you are gliding and you're only going one way, which is probably down. So we're going to make sure that you go down as slowly as possible. So let's start with a little bit of physics. So let me draw another breadstick with wings here. So if we have a glider, maybe look something like this. We've got a tail back here and another tail here. Here's our wing, something like that. We need to understand what all is acting on this glider, first and foremost. And to understand this, what I'd like to do is just start with an overview of vectors. Okay, so because I'm going to be using these quite a bit. So if I were to have different vectors pointing in different directions, and I wanted to add these together, we can do that by looking at putting one of them down first. So we go from tip to tail, so I'll draw this in a different color. And we can actually draw out what this conjoined vector might look like. And when you conjoin these different vectors, so one and in yellow, number two, and let me just mute that so that that doesn't pop up during the conversation. There we go. So if we were to combine number one and number two, as many of you probably know from your previous courses, we can figure out what's called the resultant vector by joining where we started with where we ended, right? This is just a fundamental concept to kind of understand before I start talking about the glider itself. Another kind of fundamental thing that I'd like to, again, just to kind of seed a little bit of physics background is before we even talk about the plane, let's first talk about something that hopefully everyone has some experience with or is a little familiar with. So let's say you're standing up here and you throw a baseball, right, over here. So from projectile motion, we know that this is going to fall down somewhere over here. All good because of gravity. However, if you've ever released a paper airplane and it was a decent paper airplane, you probably know that when you released this paper airplane, it flew in a more straight line, something like this. And even if you threw these with the same amount of force, let's say these are equal, the glider still went further. And so what I'm hoping to teach you guys a little bit today is why it went further and what are the important aspects that actually make this go further. So if we look side by side, now we'll go back to our free body diagram up here. And also, by the way, if I've drawn something and anyone wants me to go back, feel free to stop me at any point. I'll zoom in, zoom out. Just don't be afraid to interrupt me. I have no problem with that. So if we have our glider here and we've got our baseball over here, right? We think about what's happening when these are in the air. So let's start with the baseball. That's pretty easy. We've got gravity pulling us down, which we call weight. So when you step on the scale, you don't see 9.81 or 32.2, you see some odd pounds, right? So we measure this in weight. And that's about it. There's really nothing else going on here. We just have gravity pulling it down. If we look over here at our glider, we also have, and I'm just going to erase this so it's not confusing, We also have gravity pulling you down, which means that we have a weight. However, with the glider, something must be stopping you from falling down in this parabolic trajectory, and what's stopping you is lift. So the way that a plane works and the way that it stays up in the sky is that it's always fighting gravity. So as an aerospace engineer, the one thing that I hate the most is gravity. It fights everything. It wants to bring you to the ground, and we're always having to fight it, which is not fantastic. So because of gravity, anything that gets thrown, anything gets put in the air, we know it's going to accelerate downward. We know it's going to follow a curved path towards the ground. But if we look at this glider, what we can see is that it's more of a line path, right? It just kind of glides its way to the ground. So why is it that we have this? Again, just kind of recapping before I move along. That was because of lift. So we have weight that acts downward, we have lift that acts upward. These balance each other out. And if we can balance these out, then what you get is you get a vehicle that basically travels in an unaccelerated path. And if you remember from your physics class, what that means is that your velocity would be constant, right? So if we're not accelerating, we have constant velocity. So if we can balance these, the glider will descend at a steady speed along a constant, what's called glide path, which is basically the angle at which this is coming down, and it will not accelerate like it did for the projectile. Okay, so let me now draw this glider one more time. Hopefully this is a even better picture. Okay, so there's our glider, something like that. There's our tail, and here's our wing. Okay, let's think about all of the forces that are acting on this glider. So the first thing I'm going to do is we need to have some reference frame, right? So for the reference frame, what we'll do is we're going to see along the nose which direction is this glider going. So in this case, the glider is going down a little bit. And the reason for that is because, as mentioned before, gravity is still pulling you down. We all know that you cannot fly forever, or hopefully you guys know that, but a glider cannot fly forever, just steady level. You're always going to be descending. So this is going to be our main axis system. For reference, this is straight down, okay? So down here, we have weight acting on the vehicle, just like I talked about before. And we have another force, which I mentioned before, called lift. Lift acts 90 degrees perpendicular to the flight path, or this angle here. So this is a 90-degree angle here between these two. This is going to be our lift. And so lift is being generated by the forces. I'll talk about those pretty soon here. And the one thing that I want to consider here is weight and lift, as you can see, do not perfectly align with each other. So what I like to do is I'm going to draw another vector which goes perfectly against lift, and I'm just going to call this, just to keep it simple, anti-lift. Okay. So anti-lift is basically going to be the thing that we have to fight, right? That is the thing that the wing has to fight. All right. We know now that weight was pointing this way. We resolved some of it here, but if we do a vector addition here, we still have some component that we're missing. And what I'm going to do is I'm going to call this, even though it's really not, I'm going to refer to this as thrust. Okay. So going back to what I first started with, which was the vector addition. So let's take these. Let me change the color of this to white. So I have three different colors. We will have weight, which was in yellow. We will have our thrust, which is unfortunately also in yellow. So let me make this white. So we have our thrust. And we have this anti-lift, which I also made white. I need to make something blue now. I feel like I keep changing the colors. Make this back to blue again. Going back to where we started. Anti-lift. Okay. And what you can see is just like I drew kind of mini here, I've just expanded this out. So now we can clearly see this was weight. This component, which was kind of a question mark, is equivalent to what I just called thrust. And together, this is going to give us anti-lift. So that's how these are all kind of connected. So it's kind of a vector summation of these three forces. So all this together, we have lift, thrust, and weight. Now, for any of you who've ever stuck your hand out the window, you know that there's something that fights you back, right? So let me try to get a different color for this. We know that we also have drag, right? Whoa, what's going on here? Give me 1 second. Give me 1 second. I don't know what's going on with my pad. Try to reconnect this. Hmm. Okay. Well, I'll see what I can do to not draw a bunch of squigglies all over the place. 1 second here. Oh, I don't know what has happened to my pad, but it's become extremely sensitive. But I will try to deal with it as much as I can. Anyway, so we have drag force that fights us back. So now on our free body diagram, we have defined all of the terms that are acting on this vehicle. So let's just think for a second about what's going on here. See, I might have had a question. Yeah, I just did. I actually just did that. I unplugged it and plugged it back in. It did not help. So again, just to summarize everything, we are flying at a downward angle. We have this forward force, which I'm calling thrust, but in reality, it's not really thrust, right? We don't have an engine on this. We don't have a propeller. I'm just calling it thrust. We have lift, which is acting perpendicular from our wing. We have the weight of the vehicle, which acts down. And if we resolve that component, this gives us anti-lift. And then finally, fighting your motion altogether, we have drag. All right. Now, what is actually causing this thrust? The reason for this thrust is because think about this plane as if we were dripping water onto it. So if we were dripping water onto the top of this plane, what you would see is that it would want to beat off and run this way. Hopefully that makes sense to everyone, right? So you've probably done this if you're holding water and you tilt your hand, right? It's going to obviously fall off. So the reason for that is because gravity, which wants to come downward, is trying to find the path of least resistance. It wants to get to the ground. So this is basically the effect of gravity. So in reality, this thrust term here is truly just the effect of gravity, which is pulling the vehicle to the ground. So this is what keeps the vehicle accelerating forward. That is the only thing actually that keeps the vehicle accelerating forward. Okay. Any questions on this before I move forward? All right. So one last thing to just recap this. As you guys remember from your statics classes, we really want to have a steady, or a term you guys probably remember, equilibrium condition. And in order to achieve an equilibrium condition, we need these forces to balance. What that means is that lift must equal anti-lift and thrust must equal drag. So this is just something to keep in mind. This is the only way to not accelerate. All right, so let's move now to a term called glide ratio. Is this still readable, by the way? I know I made it a little bit less thick. Hopefully it's still Very easy to read. Okay, perfect. All right. So glide ratio, this is the single most important aspect for you, I think, because I'm pretty sure, and Dr. Hannon, correct me if I'm wrong, that you guys are being graded off of how well it glides, right? So glide ratio will tell you how well your vehicle glides. So what is glide ratio? Glide ratio is the ratio that describes how far the glider is going to travel horizontally compared to how much altitude it loses. So this glide ratio is going to be defined as basically x over y. And so these are really meaningless unless we draw out our problem. So let's think about what this looks like. So if here's our starting point, we're gliding along. Here's our breadstick plane. Drew it a little too glidey. There we go. This is going to be your x distance over your y distance. Okay, so this is going to be defined as glide ratio. So horizontal distance traveled, altitude that you lose. So one of the first things that you're probably noticing here is you need to be the tallest kid in the class. That's how you win this, right? The higher you start, the further you're going to go. That's also true. However, you could have something that starts halfway, but it has a better glide ratio, and it could go even further than the tallest person. So if you were to start here, but you had a better glide ratio, you could still get there. You start here, you could have a worse glide ratio, you still get there. So I'll let Dr. Hannon figure that one out about how to release from the same point. But the idea here is better glide ratio means you're going to go further. This slope is going to be less. So what we're trying to avoid is you start up here and you do that. All right.
You think we could get permission to launch them from the balcony or from like the over the stairs there in the in the Helmrich Center?
I think so.
I
I
think
have
so
no,
too.
I don't,
Yeah.
actually, what I'd be worried about is if they go too far. That's really
Yeah.
high up. So if your glide ratio is like 6 or 7, you're gonna hit the
Hit the glass.
you're gonna hit the glass. You might want to throw them off the staircase outside, but then you have the wind. I don't know. Need to think about it.
Yeah.
Where the best place would be. That'd be a good problem to have if you're hitting the glass. I guess that's 100. You hit the glass, you get 100.
Maybe we have somebody there to catch them and they get the height that they stopped at or something.
Mm, yep. So just to kind of quantify this, I know it's probably fairly obvious just by looking at this, but basically if you had a glide ratio of 10 to 1, what this means is that you travel, let's say 10 feet across the ground per 1 foot of altitude loss. So if you threw your glider 1 foot, you could theoretically go 10 feet in front of you. Okay. So pretty obviously here, what this means is you want to have the highest glide ratio possible. Okay. And another thing too is this distance that you traveled, X, is going to just be the height that you started with times your glide ratio. Right. Okay. So let's start to talk now about some of the aspects to achieve this, some of the important takeaways to kind of achieve this. So one thing that I want to make a note of here is what might be a little counterintuitive at first is that if you change the weight of your glider, that actually does not significantly change the glide ratio itself. And it's kind of a weird thing to think about, right? You would think if you had a glider that was lighter, it would just go further, but that's not necessarily true because it might just go faster, which provides more lift. So it's an interesting trade-off, but just something that I kind of want to mention here. If you have a heavier glider, it's just going to fly faster. If you have a lighter glider, it's just going to have to fly slower. It does not mean if you have a 50-gram heavier glider that you automatically have a worse glide ratio. It just means that you're going to get from point A to point B faster. Just something else to kind of keep in
So
mind.
so why dump fuel?
Why dump fuel? You dump fuel because on an actual jet, you have thrust, and thrust does care about your weight.
I see. Well, what if your engine goes? You don't need to dump fuel. Is that what you're saying?
Yes, if your engine goes, you do not need to dump fuel. The only reason that you would dump fuel in that case is to buy you more time.
Yep. And not
And
start a fire.
yes. Yes, and time is of the essence in that situation. So to make decisions properly, if you can buy yourself another 20 minutes of flight time, it's definitely worth it. And yes, definitely not to start a fireball, God forbid, when you land. So, all right. Any questions at this point before we move forward? Okay. So again, if weight does not directly influence your, I'm going to say GR for short, your glide ratio, then what does? So any guesses? What is going to be the most important factor then? And I'll give you all a hint. I'll go back to the drawing here.
The shape of
Okay,
your
so
wing.
you got wingspan, wing design, lift, shape of the wing, or I would call that wing design. Any other guesses? Okay. I'll give some partial credit to these. These are partially correct.
Isn't it length over the area?
Aspect ratio is what you're talking about. What does all this influence, though, at the end of the day? Well, looks like Ben got it. Drag. Drag is your biggest enemy. Drag is the reason why you have to pitch forward in the first place. Because if there was no drag, you wouldn't even need to pitch down because we don't need any thrust, right? But the more drag you have, the more you have to pitch down. The more you pitch down, the sharper your flight path angle. The sharper your flight path angle, the less your glide ratio. These are all directly connected. Okay. So your goal is to basically try to glide with the least amount of angle necessary. And the only way to achieve that is to make drag less so that thrust is less, which means that you don't have to tilt so much gravity forward. I don't know, Dr. Hannon, if you want to deal with that, but a student was asking about the attendance code. Um, so hopefully that makes a little bit of sense the way I've described that, but we want to minimize drag. So minimizing drag is our goal, and one of the ways that we can achieve it is exactly what you guys mentioned. Wing design, wingspan, aspect ratio, these different aspects, which also do influence lift, which does matter, definitely. Um, Another thing that, well, what was I going to say? I just had something in my head there. Might come back to me. But anyway, yes. So ultimately, drag. Drag is your worst enemy in this case. So let me write that out. Drag. And so what we need to figure out is what causes this? How do we minimize it? So that's what we're going to move into here. And just a couple of key takeaways here, or a couple of things that we'll probably, or not probably, we're going to talk about in just a second here. You want to have a smooth surface for your aerodynamics. You want to have an efficient wing shape, or as you guys said, design. You want to have a proper wing aspect ratio, which we will talk about. And then you want to minimize structural drag. And when I say structural drag, I mean the breadstick that I keep drawing, whose formal name is your fuselage. So a typical glider in the small scale does not need anything this big. I mean, if you think about it, why does the big, why does a plane that you fly in to go to Dallas have a big fuselage? It's because you're in it, right? If you weren't in that, there would be no need for that big fuselage. So a lot of gliders that you'll see, if I were to actually draw a little bit more of an accurate depiction, are going to look more like a very streamlined, very minimalist kind of view where you have a tail at the back with a wing and just enough here to make it basically work. It's effectively just a wing and a tail with very minimal design. And so we'll talk about how to design that a little bit. Okay. So again, just some key kind of takeaways from everything I've been talking about before we shift into more of drag. So the forces that are acting on this glider, we can represent with four simple vectors. And unlike a standard projectile, these gliders produce lift, which is what stops them from falling down straight to the earth. This is why they descend gradually. A glider, when it's in steady flight, which is what you guys are all hoping to achieve, is perfectly balanced. So you have lift equal to anti-lift, thrust equal to drag. The glide ratio is what determines exactly how far this glider is going to perform. So this is basically your performance metric. This glide ratio is also, which I'll talk about in just a little bit here, approximately equal to something called your lift to drag ratio, which I'll again talk about in just a moment. And so again, biggest takeaway here is if you want to maximize your flight distance, you really have to reduce your drag. That's the biggest killer for you. So you have to make this as streamlined as possible so that you don't have to pitch down as much and you maximize lift to drag. Okay. So let me now move on to the concept of drag since it's so important. Let me continue along here. So we're now going to move into drag. What is drag? So first and foremost, we're going to focus on three things. So we're going to talk about where drag comes from. We're going to talk about the methods to reduce drag from basically designing it smartly. That is an N, not an H. And then we're going to talk about the drag equation and the factors that influence it. Okay. So first and foremost, what I want to talk about is the different types of drag that we have. So I'm going to mention three different types of drag that we need to be familiar with. The first type of drag is going to be pressure, or sometimes referred to as form drag. The second one is skin friction drag. And the third one is going to be interference drag. And I'm not really going to cover this one very much. This one's kind of just like an FYI. That's a little bit beyond the scope of what you guys are doing, but these two in particular, you do have some control over. Interference drag is really related to lift. It's more of a byproduct from lift. So again, just a little beyond the scope. But so let's get into pressure drag. So first and foremost, we have atmospheric pressure, which we all feel all the time. And one of the things that can sometimes not be obvious, air is a fluid, okay? And this fluid exerts pressure on all objects that are immersed in it. And I say the word immersed on purpose because a lot of times we think about air as just it just sits here, right? It's just around us. But in reality, if you look at the Earth, there is a layer, which is effectively a huge ocean of air, if you will, and we live at the bottom of that ocean. But we all know that there is also an ocean here, and there's a bottom of that ocean. But here we are, down here on Earth, at the bottom of this heavy atmosphere. And so that's why when you think about pressure, sometimes you probably have heard the term standard atmosphere. We are under a 1 atm or an atmosphere pressure. That means we're at the bottom of the ocean of air, which is what we breathe every day. So it's kind of an interesting way to think about it. So let's talk about pressure for a second. So let's think about a simple circle here. So pressure acts perpendicular to all objects that it affects. It is on every single surface that touches air. Let me see if I can draw a bit of a better circle here. So every single exposed surface is going to experience some pressure. So every part of your skin, every object on your desk or in front of you, the pencil you're holding, it's all being exerted on pressure. Some of this pressure is coming from the weight of the atmosphere above us. So for example, like I said, we're at the bottom of this ocean, so we have all this air that's falling down on us. So we have some pressure due to that. This is what's called atmospheric pressure. The thing that we're used to calling atmospheric pressure, that is basically the pressure that acts down on you because you're at the bottom of this ocean of air. So that's basically that term. When the object is in stationary air, the pressure is actually fairly balanced. So that's why, for example, if you just hold your hand up, right, you don't feel any air pushing you around. So if I went back to that ball I was drawing before, well, there it goes. We're going to have pressure acting fairly equally on all sides of this, which means that if we were to do just a simple statics build up, it really doesn't want to go anywhere, right? So pressure inherently in still air does not want to do anything. But if we start to move this object through the air, this pressure becomes unbalanced. And so this is where we start to get some of these forces from. So to understand this kind of aerodynamic drag, it's really helpful to think about the flow that goes around this object. So I'll see if I can draw another circle here. So now let's imagine that we are moving. So now we're moving forward. So the air is coming at us this way. And I like to also draw the velocity. So the velocity looks like that. We're moving to the left. The air, therefore, because it just thinks it's getting hit by something, it's being seen as moving to the right. So because of the fact that we have this air coming onto this object, we're now going to need to think about what this air is going to do because it can't go through this ball, it has to go around the ball. So what I'm going to do is draw something called a streamline, which basically depicts where this flow is going to go once it encounters this object. And so if we think about these streamlines, this is basically, again, where the air is going. And so we need to think, okay, instead of the object moving, let's instead just think that someone just blew on the ball. That way we don't have to think about movement at all. So the ball was sitting here, wind came, hit the ball. So we're going to think about it that way. So this is the same as what I just had drawn. So if the ball was moving, it's the exact same thing. The important thing here is it's relative. You are the ball. If you want the ball to not to move and get hit by wind, it's the same as saying the wind isn't moving and the ball hit it. Okay, so that's just something kind of equal and opposite. But the big thing here is if you look at these streamlines, the air wanted to be straight. The object got in its way, so it had to change direction. And so what happens when you change direction? Well, this is going to change pressure. So as the airflow gets closer to this section here, to this surface that's immediately in the flow, this is going to build up pressure. So over here, maybe I'll draw this in white, you're going to have a buildup of pressure. So because of the fact that this object is forcing the air to change direction, Newton's laws are going to kick in. So the object is going to exert a force on the air, forcing it to redirect, and the air is going to exert an equal and opposite force on this object as a result of that. So the object's pushing air out of the way, so the air is going to go, well, I'll push you back. So this actually is going to produce a rearward force. So if we were to kind of draw this out, the net result of this is going to be a force in the rearward direction, which will try to push the ball back in line with the air. This actual component specifically is going to be the primary pressure or form drag. So the immediate force that's being pushed back across the front surface is going to be your form drag. So intuitively, this is kind of just leading up to the future. It's like, how could we reduce the form drag, right, of this object? If we had control over the shape, what do you guys think we could do to the shape to kind of decrease this form drag? Skinny breadstick. I like it. Yes, an Olive Garden breadstick, right, would be a little bit more aerodynamic than this ball, right? So if we were to squeeze this ball down into more of an oval, I think hopefully you can all agree that that would be less form drag because there's less air just smacking into this face, right? So the next form, and again, we're not going to talk about how to reduce it at the moment. This was just to introduce you to it. The next thing I want to talk about is going to be skin friction drag. Also, I don't know if I'm the only one who just heard a very loud crack of thunder outside, but hopefully it doesn't come here. So the other form of drag that we're going to have to fight is again the skin friction drag. So let me draw the ball one more time. As this air is being diverted around the ball, like this, the diversion itself causes air to flow around the ball or around the object, I'll say. So because of this flow, what you end up having is actually friction. So here, you're going to end up having, and not just at this point, but I'm just going to draw it here, you're actually going to have friction acting on the ball because of the fact that this air is kind of pulling along the surface of the skin. So if we were to look like microscopic, right, we would see that there's air that's actually brushing against the surface of the object. So this is the reason why you feel air, right? If you stick your hand out a window, you feel it. That is skin friction. You're actually feeling skin friction. Um, wouldn't friction act in the opposite direction? That's a good question. Wouldn't friction act in the opposite direction to the force? Yes, I suppose you're right in a more physics-based sense. Yes, but let me just think here about how to describe this because I'm describing this to mechanical engineers. I've never had pushback on this before.
Your force,
So
Dr. Comer, is in the opposite of those little vectors you just drew, right? We're moving to the left.
not quite. So relative to the ball, right? The air is moving this way. If I draw this kind of at a microscopic level, right? That's not what I meant to draw. Let me draw a flat plate. So think about it. Let me not call it friction, okay? Let me think about it like this. The air is tugging on the ball to try to follow it. Does that make more sense? Like how do I describe this instead of a force vector, right? If I have my phone and I put my headset on it and I gently pull, we agree that the headset wants to move with my hand. Does that make sense? There is friction, friction's acting in different directions, call it what you want. But at the end of the day, this is basically saying that my hand is exerting a force on the surface of this, which wants to pull it in the direction. The actual vector itself, the resultant that we see, is this friction will be parallel to the flow. So friction in this case, I drew it here. We'd also have friction here, friction here, friction here, right? So we're going to have these tangential flow pullers, shall we say. The flow wants to pull on the ball. So maybe that's an easier way to think about it. So the big thing here is it's parallel to the surface. It is opposite to the direction of motion. That is true. I think the reason why it's difficult to understand that in this point is because I said it's a stationary ball, but I suppose if you're pushing through the air, it might make a little bit more sense. All that to say, the skin friction drag itself is directly going to be a function, and I'll say the magnitude is a function of a term you guys should know, I guess, Dr. Hannon or Chris, you can tell me, of the surface roughness
Yep. Should be familiar to
of
them.
of the material that you're using slash finish. So a rougher surface is going to pull more. It's going to have more friction, more drag. A
I'm just
smooth,
unmuting to close that loop real quick
sure, go for it.
on which direction is the force. So the question was an incomplete question because you said which direction doesn't the friction act in the opposite direction of the force? Well, we have to say which force. When we define that, then we set up our boundary condition and we can say which direction we're talking about. So there's friction on the air and there's friction on the ball, and the forces we define depend on which perspective, which object you're looking at. So I think Anthony's probably used to thinking about it from the perspective of the glider, and some of you might be thinking about it from the perspective of the air. So until we define that, direction is kind of, you just use a minus sign to correct it later.
Hmm. Yeah. I guess the way I'm thinking about it is more so just what does this impart onto the glider? What does the glider feel as a result of this friction? Not necessarily that the friction acts in this direction, it's more so that the resultant force I will refer to as friction. So that might be a better way to describe it. Instead of calling this friction, you can call this just skin drag, and it acts along the flow line. Okay. So the last thing that I want to mention as another offset of the actual it's kind of directly related to the form drag is going to be the wake drag. And again, it's directly related, so I'm drawing a bit of an arrow here to the form drag. And this is going to be your wake formation, which is your rear pressure drag. So I'll draw the ball one more time.
I'm going to interrupt you again for
Go
fun.
for it.
Um, if the students put grease on the surface of uh, their their glider, does that reduce the air friction?
That's a good question. I actually would think the answer to that is no, because I think that liquids, and this might be a very incorrect statement, and I hope someone proves me wrong by Googling this, but it would not surprise me if water or liquid surfaces have a higher friction than solid surfaces, like smoother, like kind of like a metal surface. I could be completely wrong. So that's a really good question that I would love to know the answer to, because I've never purposefully put grease on any of my planes, but maybe I should.
I wonder if the lubricant is a function of, again, just this is just intuitive thought, could be wrong, but if the lubricant's a function of the surface roughness of the material that you're acting in. So like for a bearing, whatever's housing that bearing. So what we're talking about is against the air. So it's a very low surface roughness. So the grease would just disrupt. Um, yeah, like I'm thinking of submarines. I remember a fluid dynamics course where they would blow air to have like an air pocket around the submarine, and it would reduce the drag because the water has higher drag than the air.
Hmm.
Anyways, interesting statement, Dr. Han.
I think
I
so.
thought it was
My
well known, so I just figured everybody knew. Now I guess I was wrong. Sorry.
so my thought process behind this is that if you put liquid on a surface, what you would find is that the liquid will bead. It will go to the lowest pressure points, right? Yeah, it should be, you're correct, Ben. It should be a function of surface tension and density. But the liquid, if you've all driven a car in the rain and you've seen that you're up your windshield, you'll see it climb up the windshield as you speed up, right? That in part that creates beads of liquid which create these rough surfaces, which now more drag has to overcome. So my guess is that in the long term, the answer to that would be no, because a wet wing will ultimately become dry from flying, and during the process of drying will create streamlines of water, which the air now has to move. So I think the answer to that is no. It should be more draggy. But someone can prove me wrong. That's my
Dr.
hypothesis.
Hannon, give us the punchline.
Well, I was thinking about waxing a surfboard maybe as another like non Oklahoma analogy, but I need to come up with an Oklahoma analogy. But yeah, if you make the surface smoother and you're in laminar flow, that should help you. It has
Hmm.
to stay smooth, which is what Anthony was pointing out. If it doesn't, you're stuck. Golf balls are a complicated problem that I don't know if they've been completely solved. They probably have since I last checked. But these types of things, a ball in the wind is a mechanical engineering problem or an aerospace problem, depending on how you look at it. But
Hmm.
golf balls are maybe that should be simple, but still get researched in what material you make them out of, you know, how. Anyway, you could go. We could have had a golf ball design competition if we wanted, but I think what we're doing is appropriate for the tools that we have.
And I know with the golf ball, the teaser that I would say is that it has to do with skin friction drag, because the skin friction is like it's trying to pull the surface with it. So if you have a dimple, then that air becomes detached, and so it's no longer trying to pull along the surface. That's why the golf balls are better. They purposely make the flow get away from the skin so that this drag goes away. Anyway, someone can watch a great YouTube video on that, I'm sure.
Yeah. Oh, I know. Mythbusters did it to a car once, which was fun. But
Oh, I think I remember that.
yeah, I would love for one of the gliders to justify doing it to their glider. That would be fun. But we'll see. We'll see what we have.
That's a that's a NSF project waiting to get funded. Um, all right. So last little thing that I want to talk about here, as part of this kind of parasite drag overview. So this flow goes around the ball. So I'm curious, before I even start talking about this, how many of you have ever found yourself behind an 18-wheeler on the highway in your car? And I'm curious, by thumbs up here, how many of you have ever found yourself tailgating a 18-wheeler a little bit too closely? So if you want to like that, I'll like it. I'll self-report. I've definitely done that. So I put a little comment in there. So one of the things I'm curious about is for any of you who have done this, can one of you maybe describe what you felt in your car?
Like you're being pulled.
Pulled how?
Like you don't have to push the gas as much. It's just you're in the aerodynamic wake or you're before it, I believe.
Okay. So you were feeling something called slipstream, which is like a NASCAR thing, right? Like slipstream. Okay. Anything
Yeah,
else? Anyone else have any interesting things to report from being in a truck, behind a truck?
It's quite turbulent, I would say. Feeling that wake kind of, shift depending on how close or far away you are. You can feel the effect of it pretty strongly, depending on what you're driving, especially if you're in a small little car or something.
So how many of you have been in a car behind a truck like this and you feel yourself this sort of motion, this sort of swaying in your car? Like you kind of feel like you're getting pulled left and right. Like what's going on here? You ever felt that? I'm curious. So this effect that you see is due to something called von Karman vortex wake, and it ends up having wakes that do this and this and this and this, and your car gets hit left and right and left and right. And a lot of trucks, well, not a lot of trucks, but some trucks that you'll see on the road actually have on the back of the truck, so if the white part is the truck trail bed, they will have this little thing. You might have seen this before that looks like this, and it looks like a little shutter on the back of it. Have any of you ever seen this before? Looks like something that folds off. The reason for this is exactly to counter what I'm about to talk about, which is wake formation and rear pressure drag. So this flow is being forced to turn when you push on this ball. But when it comes around, right, the air will eventually detach because like nothing's holding it there, right? So this flow will begin to fall off and create these weird eddies and turbulence and vortices and all this crazy stuff that's going on back here. This creates a lot of low pressure, okay? Because everything comes down to pressure. So this creates low pressure because this was a high pressure region because we're blowing straight on this face. And in the back, the flow is getting sucked away from the face. It's getting pulled away. So if you think about the net forces, you have this huge force here, which is basically your form drag. You have these forces along the face, which if I were to draw the resultant vector, might look something like this from that skin drag. Okay. And then you have pressure that's actually lower here than it is here. And you probably all know this. Oh, sorry, did not mean to zoom in. You probably all know this already, but if you had something in between two objects, over here you're applying a pressure, and over here there's a lower pressure, this object will tend to want to do something like that, right? It's going to be pulled outward. So this negative pressure, shall we say, actually creates even more force backwards. So the intent here is how do we reduce that? How do we reduce this negative pressure or this reduced pressure on the back? How do we make the left and right sides more equal such that there's nothing trying to just suck the thing backwards even from the back, right? So this is that last kind of thing. This is your wake formation and rear pressure drag. So again, let's just summarize everything. So the total parasitic drag, which is what we're talking about here, this parasitic drag falls down to three things. The first thing is your pressure drag. This is from the form. Basically, the face that it's hitting, how ugly and how, broadside, so to speak, is the face that it's hitting. Because that's the first thing that the air is going to hit, and it's the hardest thing the air is going to hit. The second thing is going to be your skin friction drag. which is the drag caused by how far you're forcing the air to move. So if you force the air to move less, then it's going to pull less things along the way. The third thing is going to be your wake formation and rear pressure drag. So how violently is the flow going to detach once it's done with your object? Once it's got around your object, it's going to fall apart, and it's then going to create a negative pressure, which is going to pull the object back even further. So you have three things working against you, and your job is to minimize these three things. And if you minimize these three things and you make the thing stable, you're good to go. Tornado warning issued in Tulsa County. Okay.
Yeah, I was
I will,
just notified. I don't know if anybody has the weather or radar up, but be
I
nice to
can.
let at least Dr. Comer know if if he's the only one at the university to he's probably at one of the safest places. You got a basement, but just to be
I'll
aware of. It may
I'll
be a false
interrupt
alarm,
this.
but I wanted to mention that because that's something that's happening in the background.
So I'll just take a look. That is a hook echo. For those of you who don't know, that is a tornado, probably on the ground. So if you are in the region of
Yeah, that's
Sand
moving right.
Springs,
That's you. That's Sand Springs and then downtown. So you're right
okay.
in path for that.
So all of you, please be aware. I do apologize, and it's a bit ad hoc, but that is a hook echo. Um, I would be very careful. You're talking about 50 minus 7. I mean, it's at least probably EF1, EF2, so please be careful. Okay. I will also keep this on my other monitor.
Yeah,
I
the
will
tip of that
move my
tip of that
car.
little arrow there is right where HRC is. So it's just downtown side of Tulsa. I don't know how familiar you are with the map and you just moved in, but
Mm-hmm.
anyways.
Okay. Well, everyone, please be safe. Um, I'm just sorry, guys. I'm just checking the map here because I do live south of Tulsa. So anyway, I'll continue along here as long as I can. Um, if you don't mind, I'd like to just notify my wife. So just bear with me for a moment here. Okay. All right. Let's see. Where was I? Parasitic drag. Okay, yes. Anyway. So the real question here is how do we solve this problem of minimizing these three things, right? And the answer to that is a process called streamlining. We want to streamline this aircraft, or sorry, this object. So what is streamlining? Streamlining is basically shaping the object such that, let me write this out. We want to shape our object such that the airflow remains attached to the surface as long as possible. What is this going to do? This is going to reduce your flow separation. This is going to reduce your wake size. This is also going to reduce the pressure differences between the front, which we call the leading face, and the back, which we call the trailing face. So a very classic solution to this is a teardrop shape. So we'll start there with a teardrop shape solution. So let's draw a teardrop. Now I don't have it helping me, so I'll see what I can do. A teardrop might look something more like this. Okay. This is a teardrop shape. One of the things that you'll notice with the teardrop shape is that it actually naturally tends to follow along with where the flow wanted to go before it fell off the ball. Okay. That's actually where this kind of shape comes from. It's just following where did the flow want to go. All right. So in this streamlined shape, what you're going to see is that the front is going to be rounded. This allows the flow to smoothly accelerate. So with the ball, what you ended up having was the flow was coming in straight like this, and then it was being forced to basically make a really sharp turn at the last minute. But with this, we're trying to shape this, and I didn't do a good job drawing it, to be honest, but more of like that shape, right? So we're trying to go ahead and just divert the flow smoothly so that the angle doesn't go 0 to 90. We can go 0 to maybe 30 or 0 to 40, something that the flow is easier to turn around. And because of the fact that this isn't such a sharp fall off, this flow can stay attached all the way around this teardrop, all the way until it falls off. Okay. So again, the front is smooth. This lets the flow accelerate more cleanly. The body is gradually tapered towards the rear. This prevents separation. So this kind of squirrely line that I like to draw, that's going to be that separation. So what this is going to do is it's going to minimize the wake behind the object, because notice the wake is much smaller. And it's also going to dramatically reduce the pressure drag, which is the drag that built up over here. So the amount of drag that we have in this regime is going to be much less. And the drag that we have here from the pressure pulling us out is also going to be much less, which means drag got reduced. So for aircraft components, we design all of them such that they are smooth flow. So not just the wing, not just the tail. This is also going to be the design of the fuselage itself, right? All of this needs to be designed in such a way that it's going to encourage smooth flow. So there's two really important features when we're designing an airfoil or designing an aerodynamic surface at all. For the leading edge, and again, the leading edge is basically what you're seeing here, okay? So I'll call this the leading edge. We want this to be rounded as smoothly as we can. And we also want this to allow the air to accelerate smoothly around the object. So on the trailing edge, what we're hoping for here is something that is thin. So let me do trail. Oh, no, I'll draw it back here actually. On the trailing edge, we want something that's going to be thin. We want it to be tapered, which means it's gradually reducing, right? And what this is going to do is it's going to help air recombine, which means that the streamlines that I've drawn in blue are coming back together, right? They're coming back together here smoothly behind the surface.
So why do we want the leading edge to be round and not thin and tapered like the trailing edge? It seems like the air could accelerate just as fine going, in a symmetrical leading edge, trailing edge, if it was, broadly blade shaped.
Mm-hmm. Yeah, that is a really good point. So you're basically asking like, why don't we do something like this, right? Like, why don't
Right.
we do something more like equal? So the reason why you don't do this is actually because of lift, and I'm going to get there, but we have to create a large pressure differential from the top and the bottom surface. That's how lift is created. And so if we have too thin of an object, then what you end up getting is not enough pressure differential. So the airfoil becomes less effective. And we'll
So
we'll get there.
it's too symmetrical for the lift, but if we were just trying to minimize drag, it might be helpful to do that.
Correct. If you had a purely, let's say you just had like a spar or like a structural component, which was just involved in the flow, you could make that, as streamlined as possible, very, very thin, something like this, so that this is the smoothest possible thing you can do because its job is to minimize drag and not care about lift. And so right now, since we're talking about drag, what you said is exactly right. This would be a better shape than just a teardrop. And yeah, a thin piece of plastic, right, or a very thin piece of paper is like obviously the most ideal case, right? You're barely splitting anything. There's nothing else. But in the real world, we cannot use fabric, right? One of the other limitations sometimes is going to be the structural members, right? Because we have to structurally support this object. And so the thinner you make it, the weaker it gets. So you're more likely for that bending load to basically crack. Dr. Hannon also brought up a really good point, which was harmonics. So the thinner you make something, the more tendency to bend. I'm sure you've all seen that, right? Because your moment of inertia drops. And so if you bend up and you're flying around, then this thing is going to get all flexible. And then you can start getting into vibration. So it's a trade-off. Everything's a big trade-off. But in this ideal kind of theoretical that we're talking about, you're exactly right. We would want to make the front as tapered as possible and less round, because rounded objects are pretty beefy, shall we say.
Thank you.
Mm-hmm. All right. So with this information in mind, for those of you who are familiar with some aerospace aspects, you may notice this is starting to look really similar to something called an airfoil. And an airfoil is, sorry, one second, I was just updating the radar. Okay. Airfoil. So aircraft use, I just heard the alarms go off, use a specialized shape called airfoils. Also, I am keeping an eye on it, and I'm happy to give a brief update here.
Are the
So,
sirens going off?
yeah, the sirens are going off. It's still,
You guys can, I mean, Dr. Annan make that call, but I would say take cover because
yeah,
that's a beeline straight for the campus.
I would, if you live in Sand Springs, please do not watch my lecture, is what I would tell you. If you live in Lotsie, Shirk, Prattville, you need to go be with your family and be safe, is what I would tell you. This will go down probably in history, Dr. Hannon, if this is recorded, as one of your most interesting lectures, I'm sure. But yes, aerodynamics in two fronts, yeah. So please be safe. It is weakening, which is good. I don't want to go too nerdy here, but it is weakening, is what I will tell you. So let's hope it stays that way. But there's clearly still a hook here. So there's still something down, not a debris core, which is good. But anyway, I don't want to go too nerdy. All I'm saying is I'm okay for right now, but uh, if you are in any of these areas directly involved here, I would definitely be taking shelter and get off this call. All right. All right. So an airfoil, again, specialized shape, called an airfoil. What are airfoils designed to do? Solve the problem that we have, which is namely they need to generate lift, they need to minimize pressure drag, and they need to maintain the attached flow, which were basically the some of the things that we just talked about, right? So that's what these airfoils are meant to do. An airfoil, in terms of the shape, Can we get the recording? Yes, I'm sure they can. I'm sure, Dr. Hannon, you're going to share that recording with everyone. So an airfoil looks very similar to a teardrop, such that you end up having this smoother teardrop shape, if you will. So this is kind of a classical, what's called a symmetric airfoil. And so let's think about a symmetric airfoil for just a moment. The flow is moving around here, and we're going to start getting into a little bit more understanding here. And I'm just going to give a very quick teaser here about lift. This, how many of you remember Bernoulli's equation? So Bernoulli, I butchered his name. I know for a fact I butchered this name, but Bernoulli, his equations effectively were higher velocity of a flow or of a fluid means lower pressure. That's the big takeaway. Okay. Here, what we would see is that the flow is being diverged around this surface. And so as a result of this, the curvature of the flow, the airfoil is saying, hey, you need to move. This flow has to speed up. So the velocity gets higher and higher as it goes around this airfoil. Okay, so I'll draw that with this. And then it starts to taper off until it becomes back to what it was here, let's say at the baseline. So with a symmetric airfoil, again, I've drawn these as velocity vectors, but they also can represent the inverse of basically a pressure vector. So the higher the magnitude of the velocity, the lower the pressure. Lower pressure means you want to get sucked upward, right? You want to go from high pressure to low pressure. But this is a symmetric airfoil. So in a ideal situation, what you have is the total reduction in pressure up here and the total reduction in pressure up here the same. So in this condition, lift is equal to 0. You're actually not generating any lift. So that's something that's kind of interesting. Might be a little bit not confusing, but kind of surprising to think about. But just a generic symmetric airfoil in a flat condition produces 0 lift. And your drag is going to be minimal. And so here's the problem. We've solved the drag problem. We've minimized the drag problem, but if we don't have any lift, well, weight is going to take us down. And so we're going to just basically become that the baseball again. So we need to get to the lift part, but that kind of tied into the question about, the design itself. So let me now move into the actual drag equation. Okay, I think this will be one of the last things I mention about drag. So let's talk about the drag equations. All right. So the drag equation is as follows. 1/2 rho v squared s cd. Okay. How many of you have seen this before? If I just put a thing here, I'm going to put all caps drag. Can you just like this? I just want to kind of get an idea of what we're working with here. Okay. All right, good. So glad that this isn't the newest thing for everyone, but just to go over it, D, this is your drag force. Okay. Rho is going to be your air density or the density of whatever the fluid is. In this case, it's air. V is going to be your velocity of the object with respect to the flow. And that's kind of an important thing. CD is going to be your drag coefficient. And S is going to be your reference area. Okay. So first off, let's talk about every single one of these items just to make sure we have a clear picture of what exactly is contributing to that drag force that we're trying to minimize. So the very first thing that we're going to talk about is, sorry, give me 1 second, guys. I just take a call. All right. Apologize, everyone. No, it's okay. Finish the smiley, please. Hopefully it was a smiley, not a frowny. All right. So first and foremost, obviously, rho, okay? This is your fluid density. And I'm an SI guy, and I apologize, but I don't apologize for that because I don't like slugs. Drag increases with denser fluids. Okay, so easy ones to talk about is air and water. All right. Air, 1.225 kilograms per meter cubed. Does anyone know the density of water? I should know this, but I'm an aerodynamics person, so I have an excuse. Does anyone know off the top of their head? 998. Perfect. Okay. Thank you. Okay. So putting the same glider in water is 1,000 times more draggy than putting the same water in air. So kind of like what Chris was saying, right? The submarine, they try to make an air pocket because air is 1,000 times less dense. So that's density, pretty straightforward. Here in Tulsa, we're like 700 some odd feet. So it's right around, I think, like 1.1 or so kg per meter cube. Anyway, doesn't matter. Just a fun fact. Okay. For aircraft, again, we're dealing with air, right? That's a constant. Nothing you can do about it. That's the Earth, right? And all there is to it. Let's keep moving here. The next thing is going to be your velocity. Velocity is the single most important factor, or I will say it's not the single most, but it's probably the most important, one of the most important factors. And the reason for this is because it's v squared, right? So v squared means it's not as nice as density in CD and S. It's not linear, it's nonlinear. So if you speed up, it ramps up really quick, right? Whereas density and the rest, they might look something like that, right? So V is very easy to overpass the effects of the others just by creeping up on your velocity with how much drag you get. So if velocity doubles, drag quadruples, right? This is why, let's file all the way back full circle. Weight does not necessarily influence the glide time, but it does include, or it does induce the speed. You can overcome some of your glide issues by going faster, but you have to be very streamlined, right? So you have to do a better job as a designer making your drag less so that you can fly faster. So that's one of the tricky parts here. So that's one of the reasons, again, why aerodynamic drag increases dramatically once you get to these higher speeds. So the faster your glider goes, the more streamlined that you need to make your vehicle. So you have to be very careful with that. Let's keep moving on to reference area. I call it S. Some people call it A. But your reference area is going to be S. Although, again, some people call it A. This is not S over A. I'm just saying some people call it A. Drag is going to be proportional to this. And if we have a wing, okay, so for wings, the way that it's going to be defined is actually from something called a plan form view. So with a wing, actually, I'll do it here. If you have your breadstick flying along, with a tail, a vertical tail, and a wing, the reference area is actually going to be this area. So this is what we call S. So in a very simple wing, the nice thing is it's actually really easy to understand what this area is. And I do want to add this a little note here. We also include the area that's within the fuselage itself, which I know doesn't really make too much sense. That's just how we are as aerospace people. But the way that you can define this is you have a wingspan, B, and you have a chord length, C. So very simply, S is equal to B times C, right? So if you make a wing, B times C, that's your reference area. Okay. So what this means is increasing these parameters will increase your drag, right? So you might be thinking to yourself, well, why don't we just make a tiny wing, right? Well, if you make a small wing, who's producing your lift? So that's where it's a bit of a trade-off, right? The wing is producing your lift, so you can't just get rid of it. You have to create enough lift to survive. Okay. For fuselages, yeah, let me make a note on this. So for fuselages, so I did talk about wings. And when I say wings, by the way, what I mean by that is, the wing itself, which is what I drew. You also have reference area on these, right? On these tails. And then you also have some for this vertical tail. So they have their own areas. Okay. So in total, if you make an airplane or a glider, you're going to have basically three reference areas. You're going to have S of the wing, which this is what we call the wing. You're going to have S of what I call the horizontal tail, and I'll call that HT for short. And then you're also going to have the vertical tail, which I will call VT for short. All three of these components will sum together to give you a total aerodynamic drag. Your fuselage is not this area. I was just hatching it so you guys could see it, but it's not that area, so I'll remove that. This is actually called considered as the frontal area. So with a fuselage body, let me do fuselage. The reference area of your fuselage is going to be your frontal area. So if we look at I won't draw a ball. This time I'll actually try to draw something a little bit more like a fuselage. So if we had a fuselage that looks something like this, let's say, and so the wings are here and we're looking at this from the front. So our tail's back here. So here's the front, right? This is going to be your S fuse, okay? And so one of the things that you probably can start to kind of put together as you think about designing this is this S fuse is also very synonymous to, if we go all the way back up, right? This form drag. The more slender, the more clean you can make your fuselage. The thinner, the smaller you can make that fuselage, the less pressure drag you're going to get, the less reference area you have, so you get less drag. Also, on top of that, one of the things that you have to fight though is you can't just have a stick for your fuselage, right? Because you can't have the thing break apart while it's flying. It can't wobble around, right? You want it to be stiff enough to survive. So you have to find some balance of stiffness to your actual drag, right? So that's just something to keep in mind. You do not want to make a pencil thin fuselage that will just snap if you pick it up too fast. So it's a bit of a balance there. Okay, so let me talk about now the last component, which is drag coefficient. And this one I think is kind of funny. So drag coefficient, I call this the magic. This is what we don't know. This is what we don't truly understand. Why this is what it is. We just know it is what it is from experiments. So this is basically a measure of how efficient aerodynamically, well, aerodynamically, your object is. And the way that CD is defined is quite simply drag over 1/2 rho v squared s. This is why I say it's a bit of magic, because what you do is in real life, you take an object that you don't know and you experimentally figure out how much force is acting on it due to drag. You divide that by 1/2 rho v squared s, and this gives you the magic number, which is your drag coefficient. So if someone tells you I have a drag coefficient of like 1, not too good. If someone says I have a drag coefficient of like 0.03, really good, right? The intent here is this is a measure of your drag force to your dynamic pressure force effectively. So that is what this is. And it depends on the shape, it depends on the surface roughness, it depends on the orientation of the flow conditions itself. But the big thing here is you want to minimize CD through smart design using some of the things that I mentioned before. So if you reduce the coefficient of drag, this is probably one of the most effective ways that you're going to improve this. Can you label magic as experimental data? Sure. There you go. Experimental data. Okay. Yep, not a problem. So one of the things that I would kind of give you a practical example of, and I can't really like show this, but I can give you just an example of this is if you were to create a wing, and let's say because of your limitations on what you could do with your manufacturing methods, you made a wing that looked like this, and then you made a wing that looked something like this, and you had them fly. So you had these glide. What you would find is that this wing, because it's more streamlined, because of this tapering, right? Because of this kind of curving and this shaping, will travel quite a bit more. And even in a flat plate example, which is kind of like the simplest solution, what you'll see is that even doing some simple like chamfers, if you will, with like a little bit of filleting, you can receive or you can improve up to about 30% of your glide distance just by adding something as simple as this. Okay. So that's how important some of these aspects are. And you can hopefully, because of the things I've talked about, it kind of makes sense why, right? This has a lot more pressure drag. We can tell that. This is also going to have more streamline drag, right? And it becomes obvious, like if you just kind of draw out the flow in your head, right? It starts to become a little bit more obvious. So start to think in terms of the streamlines, right? Or if you were to drip water in front of this thing, how might it go, right? That's kind of what you're starting to think about. Okay. Any questions on the drag before I go into lift? And I might take maybe a 5-minute break if that's okay with everyone. Been talking for a little bit. So, but any questions on drag at all? All right, it's an Amber Alert. Any questions, or sorry, tornado warning alert. Any questions on this? I apologize if you can hear that. Okay, so I'm going to kind of take a little bit of a break here, just for myself, and I will get back to all of you very soon. I'll keep the stream up. I'll still be talking. I might just keep this radar up for everyone so you can all see it, where everything is going. Again, if you're in Sand Springs or around this area, please stay safe. Um, so, yep.
So if we run out of time today, I think one thing that's maybe the most useful is to provide some, hints for resources on, how to learn where to put your tail, what angle to put your tail, how to curve your wing. Where can they learn that stuff?
Okay.
we can't get it all done today.
Sure. Yep. Good points. And the class ends at, is it 7:10, if I'm not mistaken?
Yeah, it's a little bit flexible because I like to give them plenty of time to meet with their teams.
Okay,
Once,
got you.
once we've covered the material, they can meet with their teams after that. Again, stay safe, but
Okay,
yeah.
got you. Understood. By the way, for anyone interested, this is a free application weather-wise. They have an app as well. It's very helpful. This, if for any of you, we all live in Oklahoma. I feel like this is useful information. Um, if you ever see a cell or a storm that looks like this, they call this a hook echo. You need to be taking shelter. What this is basically the tornado wrapping the entirety of rain around itself. So it is literally pulling, because it's so strong, it's pulling the air around it. So this is basically the way that the flow is moving into the tornado, which is here. And this opening here is called your inflow. So we have cold air coming in here, or maybe it's warm air, I'm sorry, warm air coming in here to feed the storm. And then the rest of the air is falling down violently through the tornado and getting sucked in. So it's a very, I might have gotten that reversed, but anyway, it's a very violent thing to see. So if you see a hook echo like this, um, it is happening. And I may need to go. So I may put this on hold, Dr. Hannon, because I just realized I am right here. So I think I'm going to go ahead and call it if that's all right. And I'm happy to make a recording and share it with your class on lift and tail, and I can share that with them if that's all right with you.
Oh yeah, I'm not. The last thing I'm going to do is put safety second. So
Okay.
that for design, guys. Whatever you design, safety should be first, including your team. Right. So we're just going to demonstrate that here today. I think that's a good lesson for all of us.
All right. If the recording, I don't think it's on my computer, but whoever has the recording could please share. Ben, no problem. I think I have plenty of time to just drive west and go home. But I do appreciate the offer. Because I don't want to deal with my car getting destroyed. So I'll just drive away. But if I was in Sand Springs, I would not be driving, that is for sure. But I think I've got plenty of time. This is actually moving quite slow. But yeah, anyway, so everyone please be safe. Um, yeah, please be safe. And if you have family in Sand Springs or North Tulsa, uh, Sperry up here, take it seriously. This is no joke. This is an actual tornado. So please take this seriously. All right. Uh,
This,
thank you all.
this was great. They got to see your teaching style too, which is fun, and really appreciate you coming by. So I'll let you go. I don't want to keep you. So everybody, stay safe and have a great weekend.
All right. Thank you all.
Thanks,